Hi, welcome back to Educator.com, and today's lesson in general chemistry is on atoms, molecules, and ions. We're going to go ahead and look at the lesson overview right now. We're going to get a brief introduction into atomic structure, which is more of a historical background. Following this, we'll get into what we mean by isotopes. We'll get introduced to the periodic table in this lesson, followed by naming compounds. Basically, ionic compounds, those that are made from metals and nonmetals, polyatomic ions, hydrates, and also what we mean by molecular compounds. We're then going to get associated with the concept of the mole and how that can be used to determine what is called a percentage composition, which is going to ultimately lead to the finale of this lesson, which is on determining what is known as the empirical and molecular formulas. All right. By the beginning of the 20th century, physicists had already known the following. Number one, that opposite charges attracted and that like charges repelled. And number two, a subatomic particle existed that was negatively charged, which had been called the electron, commonly abbreviated E-. And one of the first accepted models of the atom was called the Plum pudding model. And what the Plum pudding model was the following. It was essentially a sphere of positive charge, and embedded in the sphere of positive charge were the subatomic particles, the electrons. And these were completely stationary, if you will. But there was no accounting for any other type of subatomic particle. So once again, this is called the Plum pudding model. So a sphere of positive charge that contain electrons scattered throughout. We now get into one of the earliest theories that was accepted to explain for atomic structure. This was called John Dalton's atomic theory. John Dalton's atomic theory contained the following premises. Number one was that matter was composed of individual units called atoms. And number two, that these atoms were the smallest unit possible and that they were indivisible. That is, we could not break them down any further. Okay, so atoms were indivisible. Okay, number three, the third premise of John Dalton's atomic theory was that atoms of one element were all identical to each other. Number four, atoms of one element are going to be different than atoms of another element. So that's what we reference chemical identity, right? Okay, so atoms of one element different than atoms of another element. And finally, the fifth and final premise was that when elements combine, they can combine in small whole number ratios to form compounds. So atoms combine in small whole number ratios to form compounds. And this fifth premise here is going to be looked at again, and that's what we call the law of multiple proportions. Okay, I'm going to go ahead and put an asterisk next to each of the premises, which we actually find not to be so true today. Atoms were indivisible. Well, that's not true because we can divide an atom in a process called nuclear fission. And so premise 2 is not completely accurate. And the next one is atoms of one element are all identical to each other. We're going to talk about this is that not all atoms of the same element are identical, because atoms can exist in different forms, which we call isotopes. So that's going to be coming on later on. All right. Following John Dalton's atomic theory was one of the first major experiments on atomic structure, and this is what we call Ernest Rutherford's gold foil experiment. What Ernest Rutherford did was the following. He shot a beam of high energy particles that were positively charged, and these positive charged particles were called were what we call alpha rays, and this was shot at a very thin piece of gold foil. Now, what was the expected result? The expected result was the following, that all of the alpha rays should have gone straight through. Why? Because the positive sphere was mostly empty space, and that the positive rays should have been attracted to the electrons that are embedded in the sphere. So this is expected result due to plum pudding. However, the actual result was the following. From the gold foil, yes, the majority of the rays did indeed go straight through. However, what was determined was that some rays actually got deflected at various angles, and you would actually have a couple rays get deflected completely backward. Now, this was highly unusual because this was not predicted by the plum pudding model. Instead, what came about was the following implication. And the implication was the following, that matter and atoms contained a dense center of positive charge, because it's positive charge that was making the alpha rays deflect. And this positive charge is what we today refer to as the nucleus. And the nucleus is at the center of all atoms and is positively charged. So, to re-summarize, the implications of the gold foil experiment was that all atoms have a dense center that is positively charged, which we call the nucleus. Inside the nucleus, two subatomic particles exist. The proton is positively charged and the neutron has zero charge. Number 3, the nucleus is responsible for the mass of the atom. That's what gives an atom weight. And finally, electrons, which were already known to have existed, exist outside the nucleus and have negligible weight. And so let's go ahead and summarize these subatomic particles. Okay, neutron, okay, proton, and electron. Now, please make a note that these relative masses and the relative charges, okay, are indeed in relation to each other. And so a neutron is going to be assigned a mass of 1 and a charge of 0. A proton is assigned a mass of 1 and a charge of positive 1. And an electron has a negligible mass, a mass of 0, and a charge of negative 1. And of course, we symbolize the neutron lowercase n, proton p, and the electron is going to be e. All right. Now, another fallacy, one fallacy in John Dalton's atomic theory was that atoms of the same element are all identical to each other. But we're going to learn that atoms of the same element can exist in different forms, and these are called isotopes. And isotopes are the same atoms of the same element, and they differ only in their number of neutrons. And so number of protons is going to be equal to the number of electrons. And this is because of charge neutrality. But the only difference is the number of neutrons. So number of n differs. And so now we're going to introduce something called isotope format. Okay, so for example, carbon has two isotopes, carbon 12 and carbon 13. Now, anytime you see the number immediately following the hyphen, this is what we call the mass number of the isotope. And the mass number of the isotope is simply equal to the number of neutrons plus the number of protons. And so when we write an isotope in a specific format, it's always going to have the following design. Okay, element symbol X, A on top, and Z on the bottom as a subscript. Okay, so X is simply your element symbol. Okay, A is your mass number, and Z is simply your atomic number. And the atomic number is strictly equal to the number of protons of the element. Okay, so now a mathematical relation follows that if you take the difference of A minus Z, you're going to get the following: the number of neutrons plus the number of protons, and then minus the number of protons. And as you can see, protons cancels. And so when you take the difference of A minus Z, you simply get the number of neutrons, everyone. So for example, if you take 12, 6, and carbon, okay, we have 12 is equal to the number of neutrons plus the number of protons. Okay, 6 is on the bottom, and that's the number of protons, which is also equal to the number of electrons. Therefore, A minus Z is equal to 6, and that's equal to the number of neutrons. And so carbon 12 has 6 protons, 6 neutrons, and 6 electrons. However, if you do the same analysis for carbon 13, we're going to get 6 protons, 7 neutrons, and 6 electrons. So as you can see, isotopes strictly differ by the number of neutrons present inside the nucleus. And now we get introduced to the periodic table. Well, the periodic table is essentially organized into different rows and columns. Okay, so each column is also referred to as a group. Okay, each row is referred to as a period. And typically there's always a staircase that is embedded in all of our periodic tables. Anything to the left side of the staircase is what we call a metal, and anything to the right side of the staircase is what we call a non-metal. Now, when we look at the periodic table, you see always the following. Okay, you see a number on top. The number on top is what we call the element number. And the element number is actually the atomic number, number of protons. Okay, the number on the bottom is the atomic mass of the element. And finally, right in the middle is your element symbol. We're going to talk now more about different areas of the periodic table. Now, we talked about metals, and metals have the following characteristics. They appear lustrous, which is shiny. Okay, they are good conductors of heat and of electricity. They are malleable, which means we can form thin sheets out of them. And they are ductile, which means we can pull them into fine wires. Non-metals are going to be the opposite. They're going to be electrically and thermally insulative, which is what we mean by poor conductivity. In addition, they are brittle, which means that if we take a hammer and hit them, they are going to crumble, and instead are not too malleable. Okay, so will crumble. Okay, but right in the middle, of the border between metals and nonmetals. That is what we find semimetals. Okay, semimetals are also known as metalloids, and these they border that staircase that we drew previously. Okay, so border the staircase. And because they are called semimetals or metalloids, they are going to have properties of both. They tend to be good conductors of electricity, but poor conductors of heat, and they tend to be malleable. And the typical examples are, of course, silicon and germanium. And we see these two being used in a lot of electrical devices and what we call semiconductors. All right. Now, what we're going to analyze next are some of the major columns of the periodic table. Okay, group 1 is what we call the alkali metals, such as lithium and sodium and potassium, etc. And group 1 metals tend to have the following characteristics. That is, they're moisture sensitive, which means they have a tendency to react with water, and they can be explosive when they react with water. Group 2 are what we call the alkali earth metals, okay, such as calcium and magnesium and barium, and these are harder than group 1 and less moisture sensitive. Okay, group 6 are the halogens, which are fluorine, chlorine, bromine, and iodine, and all of these occur naturally in nature diatomically, which means they occur in pairs. So when someone says fluorine, it's really F2, and Cl2, okay, Br2, and I2, and the halogens are incredibly reactive. Finally, group number 8, the rightmost column of the periodic table, are what we call the noble gases, such as helium and argon and neon. And unlike the group 7s, these are going to be monatomic. That is, they occur just as individual units, and they are called noble gases because they are relatively inert and have a smaller tendency to react. Okay. Now that we've been introduced to the periodic tables and the elements that comprise them, let's now talk about different types of compounds. The first type of compound we're going to study are called ionic compounds. Ionic compounds are formed between a metal and a nonmetal, or they contain what are known as polyatomic ions. And because of the strong electrostatic attractions that exists between opposite charges, ionic compounds tend to have very high melting points. And below are a couple of these polyatomic ions. So polyatomics could be the following, something like Cl32-, which is called carbonate, okay, or SO42-, which is called sulfate. Okay, NO3 1-, which is called nitrate. So you see why these are called polyatomic ions, because it's several atoms coming together to form one entity. Okay, so those are what we call polyatomic. Now, that is different than monatomic ions, of course, which are just formed from one unit, something like Cl-, O2-, Al3+, etc. Okay, some polyatomic versus monatomic. And it turns out that we can actually use the periodic table to predict the ionic charge for main group elements. And main group elements are going to be group 1 and group 2, and then group 6, group 7, and group 8. Excuse me. Group 3, 2, 6, and then 7 and 8. And it turns out that all of the group 1s, okay, tend to form a 1+ charge. All of the group 2s tend to form a 2+ charge. Group 3s tend to form a 3+ charge. We're going to skip 4 and 5 because they tend not to form ionic compounds to such a large degree. And so column 6, we're going to get a 2- charge. Column 7 is going to be a 1- charge. And group 8 we say no charge because group beta are the noble gases and they tend not to react with other species. Now you notice also, very importantly, that the positive charges, which are what are called cations, okay, these are going to be formed by metals, and that the negative charges are what are called anions, and these are all non-metals. Okay. Oh, I'm sorry, I'm leaving out group 5, everybody. Group 5 is, of course, this is going to be a 3- charge. Okay, so you have your cations and then your anions. So once again, cations are going to be formed by metals, and anions are going to be formed by non-metals. Now, we have to learn how to name ionic compounds, such as NaCl, such as BaF2. And so we need to now go over the systematic procedure for doing so. Okay, so we're going to first you're going to name the cation first, followed by the anion. And the anion will end in IDE. So something like NaCl. Okay, so the cation is simply going to be sodium. And Cl, okay, is usually chlorine. But now we're going to become chloride. And so the correct name of NaCl is simply sodium chloride. Very simple. Okay. You do not use prefixes mono, di, tri, etc. to denote subscripts in a formula. So something like, for example, BaF2. Okay, let's go ahead and name it. So that's going to be barium followed by fluoride. Okay, and you do not say difluoride. No difluoride. So for example, again, we ignore the prefixes. For certain transition metals, you're going to use a Roman numeral in parentheses to indicate the metal charge. So if we want iron 2+, we're going to denote it as iron Roman numeral 2. And iron 3+ cation is going to be Fe Roman numeral 3. And again, you should definitely ask your instructor as to which transition metals he or she would like you to know for sure, where you have to use a parentheses to indicate charge. Finally, you can also have a hydrate. And a hydrate is when you have water attached. So for example, Cl2 dot 5 H2O. So we're going to use the prefixes followed by the word hydrate. So 5, using the Greek prefix, would be penta. And so we would just say that this is the pentahydrate compound of ClCl2. Okay, let's go ahead and put everything together and do a couple of examples. Okay, so Al2O3. Okay, FeCl3. Cu(I2.3H2O). Okay, so we're going to name the cation first. So Al2O3, that's going to be aluminum. Okay, followed by oxygen becoming oxide. Okay, FeCl3, so Fe is one of those we need to know. So iron, something in parentheses, and then chlorine becomes chloride. Now we have to come up with the charge. Okay, so each chlorine is a 1- charge, and there's 3 of them, giving me a 3- overall. And so for iron's going to be 3+ here. So giving us iron Roman numeral 3 chloride in the end. So don't forget, for the ionic compounds, the net charge should equal 0 to maintain charge neutrality. Okay. Right here, we're going to have copper. Copper is one of those you need a Roman numeral for, followed by hydrate, followed by iodide. And then we have 3 waters, which becomes trihydrate. And here, iodine is a 1- charge, and there's 2 of them, giving me -2 overall. And so copper must be a +2 to balance it. And so I'm going to indicate that in the parentheses as Roman numeral. Now we got to do it the other way. So before I gave you the formula and you were asked to provide the name. Now let's go ahead and write the name given, write the formula given the name. So let's go ahead and look at the following examples. Okay, so barium phosphide. Okay. Ammonium phosphate. Okay. So now barium phosphide. Okay, barium is Ba. Okay, phosphide is phosphorus, which is P. Now what I like to do is I like to put the charges up in the top, just for my own purposes. So barium is 2 plus, phosphorus is 3 minus. And what I always tell my students to do is then I use the crossing rule. Basically, if you cross the charges, they become the subscripts for each of the other elements. And so Ba is going to get a subscript of 3, and phosphorus is going to get a subscript of 2. And you can convince yourself to make sure that the charges cancel. 3 of the bariums times 2 positive, plus 2 of the phosphorus times 3 minus, and yes, they do cancel to 0. Okay, next one is ammonium phosphate. Ammonium is NH4. Okay, phosphate is PO4. Okay, ammonium is a 1 plus charge. Phosphate is a 3 minus charge. Let's go ahead and cancel and cross them again. Okay, and when we cross them, we're going to get NH4, 3, and then PO4 with a 1. And let's go ahead and make sure that they all work out. So 3 of the ammoniums times a plus 1 charge, plus 1 of the phosphates, and a 3 minus charge. And yes, it does cancel to 0, everyone. Okay, so that's some nice properties on ionic, nice sample problems on naming ionic compounds. The other type of compound we're going to learn about now is called a molecular compound. And molecular compounds are not a metal and nonmetal, but instead they are composed from 2 nonmetals, something like CO2, something like CO, and of course H2O itself. Now, to name a molecular compound, the names, the rules are going to be very similar, with just one main exception. We're going to name the element, first element first by its entire name, and then the second element has an IDE suffix. And this time we do pay attention to the subscripts. We're going to use the Greek prefixes mono, di, tri, tetra, etc. to determine what the subscript is. However, you omit mono for the first nonmetal. So something like CO2, name the first element first, which is carbon. Okay, the second element is oxygen, becoming oxide. And there's 2 of them, which is how we come up with carbon dioxide. Okay, something like N2O5. Okay, so there's 2 nitrogens, which is di, and the first element gets the full name, so dinitrogen, and then 5 oxides, which is pentoxide. So actually naming a molecular compound is always easier than naming an ionic compound. Why? Because you don't have to worry about charge. Now, on to what we call the concept of the mole. When you go to the supermarket and you purchase eggs, they are always in either a half dozen or a dozen. It's very hard and very seldom that you're going to purchase just an individual egg. It's convenience. It's convenience for us to refer to eggs as a dozen. And so for chemistry, we have the equivalent of our dozen. And the mole is our chemist's dozen for convenience. When you go into lab, you don't measure just the weight of, for example, one atom. You don't deal with an individual atom. It's not practical. So what the mole is all about is that it goes from the micro scale to a more macro scale, and it's more practical. And basically our dozen, which is what we call the mole, and the mole is abbreviated simply MOL, is equal to the following: 6.022 times 10 to the 23rd units of whatever you are measuring. So this is equivalent to saying 1 dozen is equal to 12 units of whatever you are measuring. Okay, so again, our dozen, the chemist's dozen, is what we call the mole. And this mole is probably this number you have to memorize, I'm pretty sure. And 6.022 times 10 to the 23rd is what we call Avogadro's number. Okay, Avogadro's number. Now, the mole we're going to find is a central unit, and it can connect the following quantities. The mole, we can go and calculate individual units. The mole, we can also get what are the grams. Now, when we go from mole to units, we are going to multiply this way by Avogadro's number, 6.022 times 10 to the 23rd units for every 1 mole. But when we go the opposite direction, we're going to divide. Okay, we're going to divide by 6.0. We're going to divide by Avogadro's number. Mole can also be used to go to mass. And so when we go to mass, we can actually multiply the mole by a rate conversion factor of gram for every 1 mole. And when we go the opposite direction, we're going to divide by 1 mole. We're going to divide by grams. So we can see that mole is truly a central unit, and the conversion factor of gram per mole, that's what we call the molar mass. And this is equal to the grams that 1 mole of a substance weighs. Now we're going to come back to this quite heavily, and we're going to do a lot of example problems utilizing the mole. Now, where do we get this molar mass from then? Well, on the periodic table. Okay, so on the periodic table, atomic masses, remember it's the number below the element symbol, are also called molar masses. And so when you look at C612.01 on the periodic table, this bottom number here is the molar mass of carbon. And so 1 mole of carbon weighs exactly 12.01 grams. That's how you write it out. Now that's going to be a conversion factor. So how many moles are in 25.7 grams of sodium? So you say 25.7 grams of sodium times something over something, and that's going to give us moles of sodium. All right, so remembering our dimensional analysis now, grams is going to go downstairs of sodium, and moles of sodium is going to go upstairs. And so you just look up the value, and that's going to be 22.99 grams of sodium for every 1 mole of sodium, giving you your answer in units of moles of sodium. Let's now go ahead and utilize Avogadro's number. How many atoms are in 1.2 moles of carbon? Okay, so 1.2 moles of carbon times something over something is going to give us our answer in units of atoms of carbon. Okay, so to get canceled, moles of carbon goes downstairs, and then atoms of carbon goes upstairs. And so we know from our flow chart with the mole that this is involving Avogadro's number. So 1 mole go downstairs, and 6.022 times 10 to the 23rd atoms goes upstairs to give us our answer in units of atoms of carbon. All right, so whenever you see the word atoms or molecules, that's pretty much a good giveaway that you're going to be using Avogadro's number as your conversion factor. So again, always keep a mind into that, and especially if the word moles is mentioned too. All right, now that we've been introduced to what the mole can help us get, we're going to find something else, that the mole can be used to calculate what's called molar mass of not only an atom, but also of a compound. Let me say that again. The mole can be used to calculate the molar mass of a compound. Excuse me. The molar mass of an element is already provided to us on the periodic table. And basically, the molar mass is simply the net sum of all molar masses of each element. And so the molar mass of carbon dioxide is simply equal to the molar mass of carbon plus the molar mass of oxygen plus the molar mass of oxygen, because we have two oxygens. So that's going to be equal to 12.01 grams plus 16.00 grams plus 16.00 grams, giving us a grand total of 44.01 grams. And so 1 mole of CO2 weighs exactly 44.01 grams. Having said that, we can also use molar mass as a conversion factor for a compound. So how many grams are in 1.2 moles of carbon dioxide? 1.2 moles of CO2 times something over something is going to give us our answer in units of grams of CO2. Okay, so the mole is going to go downstairs and the grams is going to go upstairs. And right there in the previous problem, we calculated this conversion factor, our molar mass of CO2. Anytime you want to relate mass and moles, it's always molar mass to be your conversion factor. And so it's going to be 1 on the bottom, and it's going to be 44.01 on top, giving us our answer in units of grams of CO2. Now, the next application of the mole is what we call percentage composition. And so percentage composition is given to us to be the following. Okay, so percent composition of an element tells us basically the parts of the element divided by total parts times 100. It basically tells us your relative amount that a specific element makes up of the compound. And so this equation that we actually use is going to be then be the total mass of the element divided by the molar mass of the compound. All of that times 100. So let's go ahead and answer this question. How many grams of carbon dioxide are contained in 65.1 grams of CO2? So this problem is strictly wanting to know how much carbon is going to be contained in so much CO2. So let's go ahead and first calculate the percentage composition of carbon in CO2. So we're going to say 12.01 grams, because there's only one carbon, divided by the entire molar mass of CO2, which is 44.01 grams times 100, and that's going to give us 27.3%. So carbon dioxide is only 27.3% carbon. The majority is oxygen. Now, that tells me that any sample I hold of CO2 in my hand, 27.3% of that is carbon. So we're going to use percentage as our conversion factor. And so we're going to say 0.273 times the 65.1 grams of CO2 is going to give me my grams of carbon. And we're going to get 17.8 grams as our answer. So once again, anytime you see a problem that relates the amount of an element contained in a certain amount of compound, you want to use percentage composition as your tool. Finally, we're now going to see how we can determine what's known as an empirical and molecular formula. An empirical formula is the simplest whole number ratio of a formula. So for example, CO2. This is an exact 1:2 ratio of carbon to oxygen, and that's my smallest ratio. I cannot go smaller than that. However, let's go ahead and look at one that's maybe C2H6. In this example, I have a ratio of 2 to 6 of carbon to hydrogen. But you notice that I can divide. I can divide by a lowest common denominator, a lowest common multiple, which is 2. And I'm going to get 1 to 3 ratio instead. Therefore, 1 to 3 is actually my smallest ratio. And so that's going to be CH3, which is my empirical formula. So what we're going to do is we're going to determine how to calculate the empirical formula. And the empirical formula is determined from elemental analysis. Basically, you have an unknown sample, and you put it through, you perform what's called an elemental analysis test on it. And after you perform this analysis, you're going to get a printout of the percentage that a certain element makes up in your unknown. So you're going to get X percent of, for example, carbon. You're going to get Y percent of, for example, oxygen. And you're going to get Z percent, for example, hydrogen. So these percentages, again, are only to be used for empirical formulas. They may or may not necessarily give you the actual formula. Only the relative amounts are reported. Now, if you want to get the actual formula, which is known as the molecular formula, you can determine it, but only if the molar mass is already provided for you. Let's go ahead and look at a typical example. Okay, so a compound used as an additive for gasoline to help prevent engine knock has the following percent composition by mass: 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen. The molar mass is known to be 98.96 grams per mole. Determine both the empirical and molecular formulas. All right, now the very first step is to get your percentages into grams. Okay, so get percentage to grams. And after we get everything into grams, then we can go to our central unit from the chapter, which is moles. Again, whenever you're in doubt, get the moles. Now, the nice thing about percentages is that percentages always mean out of 100. So if we assume 100 gram of compound, the percentages automatically become grams. And so we have 71.65 grams of chlorine, 24.27 grams of carbon, and 4.07 grams of hydrogen. Again, assuming 100 grams of compound. Okay, so now we're going to go ahead and get to moles, and this is something we know how to do by now. So when we go ahead and get to moles, we're going to get 2.02 moles of chlorine. We're going to get 2.02 moles of carbon, and we're going to get 4.04 moles of hydrogen. Okay, so step 1 is done. Okay, now step 2. Step 2, we're going to take our moles and we're going to divide. We're going to divide by the smallest moles present. Okay, so divide by smallest moles present. Everything. And we're going to get a nice whole number that is going to become our subscripts in our empirical formula. Okay, so the result is the empirical formula subscript. So when we take chlorine and divide it by the smallest number, which is 2.02, we're going to get 1. Carbon divided by 2.02, get 1. And for hydrogen, 4.04 divided by 2.02, we're going to get 2, giving us our empirical formula of CH2Cl. Okay, now, what happens if you don't get a perfect whole number? What if you get 1.5, comma 1.5, comma 2. Well, Dalton's law of multiple proportion tells us that we cannot combine elements in other than a small whole number ratio. So basically, anytime you have a decimal number, well, we're just going to then multiply everything by the same factor to get everything in whole numbers. And so when we do that, we can multiply 1.5 by 2 and everything by 2, giving us nothing but whole numbers, 3, 3, and 4. So if that happened, then those numbers would become the empirical. We would get CH3H4Cl3. All right, now, to get the molecular formula, you simply do the following. You take the molar mass of the molecular formula, which is given to you, and you divide it by the molar mass of your empirical formula. And that is always going to give you a nice whole number. And when we do this, we're going to get 98.96 divided by our molar mass of our empirical formula, which is CH2Cl. And we actually get 48.468. And when we do this, we get approximately 2. You take that whole number and you multiply the subscripts of the empirical formula by this. And so I get our molecular formula of C2H4Cl2, which is the formula of the actual compound. And you can always double check your work. You can add up the molar mass of C2H4Cl2 and we're going to get very close to 98.96. Alright, let's go ahead and summarize. Okay, atoms are composed of a central nucleus that is positively charged. Protons and neutrons reside within the nucleus and electrons are outside. We saw that isotopes of the same element differ only by their number of neutrons. And we went through specific rules for naming ionic and molecular compounds. We also saw that the mole is a central unit that allows for conversion between number of atoms and molecules and for mass. And finally, the mole is a central unit that is required for several types of different problems, including percentage composition and the empirical and molecular formula problems. All right, let's go ahead and look at some sample problems. You have 1 milligram of lithium metal reacting with molecular fluorine gas, and the resulting fluoride salt has a mass of 3.73 milligrams. Determine the empirical formula of lithium fluoride. Well, you have 1.00 milligrams of lithium, and after it reacts with the molecular fluorine gas, which is F2, you get 3.73 milligrams of your lithium fluoride. Well, if I start with only 1 milligram of lithium and I wind up with 3.73 milligrams of compound, why did my mass get heavier? The mass got heavier because it reacted with fluorine. Fluorine came on board. And so we can actually determine the mass of fluorine. And that's just the difference. 3.73 mg minus 1.00 mg. And that's going to give us 2.73 mg, which is the mass of fluorine reacted. Okay, so we got all of our masses now. Now let's get everything into moles. And so 2.73 milligrams of fluorine is going to become 1.44 times 10 to the negative 4 moles of fluorine. 1.00 milligrams of lithium is going to become 1.44 times 10 to the negative 4 moles of lithium. Now that we have all of our moles, we can divide by the smallest number present, and for this problem they are identical. And so when we divide everything, we're going to get Li1 and F1 for our empirical formula, or just LIF. And this answer actually makes sense because we know that lithium is a 1 plus charge and that fluorine is a 1 minus charge. And so indeed, the charges do balance each other out. And now moving on to sample problem 2. How many atoms of carbon are present in 2.67 kilograms of C6H6? So in this case, we are asked about an element within a certain compound. Well, that sounds a lot like percentage composition. So let's go ahead and calculate the percentage composition of carbon in C6H6. Okay, so the percentage composition is equal to the total mass of carbon. There's 6 of them, by the molar mass, 12.01, divided by the total mass of C6H6, which is 6 by 12.01 plus the 6 hydrogens by 1.008, and all of that times 100. So when we do this, we get 92.3%. So C6H6 is mostly carbon, 92% carbon. Okay, so remember what we did last time. We're going to take our percentage composition, 0.923, and we're going to multiply it by the total mass, 2.67 kilograms, and that's going to give us the 2.46 kilograms of carbon in this specific sample. Now the question is asking for atoms of carbon though. So somehow we have to go from kilograms to atoms. Well, remember, anytime you see the word atoms or molecules, it's going to be via an Avogadro number. So our first step is to go from kg just to regular G, and then from G to the central unit, which is moles, and then of course moles on to atoms. And we can go ahead and do this. So we're going to say 2.46 kilograms of carbon times something over something. So G goes on top, kg on the bottom. That's going to be 10 to the third G over 1 kg. And now on to moles. So times something over something. G's goes downstairs to get canceled. Moles goes upstairs to get carried through to the final answer. And that's molar mass. And so you look up the molar mass of carbon, which is 12.01 grams for every 1 mole. And then finally, times something over something, giving us our answer in atoms of carbon. So that's Avogadro's number. So mole on the bottom and Avogadro's on top, which is atoms here. And that's 1 mole on the bottom and 6.022 times 10 to the 23rd atoms on top. And you should get an answer of 1.23 times 10 to the 26 atoms of carbon. Okay, so I want to thank you for your attention, and this concludes our lecture on atoms, molecules, and ions. And thank you for using Educator.com.